So I welcome all of you. Let us look at the rate constant and its significance. As you already know, for any reaction of type A plus B gives rise to C, you can write XAYB and ZC. Rate is equal to K into A to the power small a, B to the power small b. You know that A, B are orders with respect to A and B respectively, and they may or may not be related to X and Y, the stoichiometric coefficients. I am not worried of that now. I am more worried of this K. What is K, sir? You know very clearly that rate is equal to K if concentration of A is equal to concentration of B is equal to 1 mole per liter. So when the concentration of reactants are taken as unity, the rate corresponds to the value of rate constant. And now, for a given reaction at constant temperature, rate constant is constant. It means if I double the concentration of the reactants, namely A or B, or if I make the concentration of A half or one fourth, whatever, there would be no change in the value of K. As you already know, the apple, if each apple costs you 10 rupees, the cost per dozen apples is always 120. Whether you are buying 100 apples, 200 apples, 300 apples, whatever, or 2 apples, cost per dozen always remains a constant. Like that, the rate constant always remains constant and it is not dependent on the concentrations of the reactants you would take. However, rate constant K depends on temperature. If you vary the temperature, of course rate constant varies. Are we very clear about it, sir? Now, third aspect, the units of rate constant can be written as moles per liter whole to the power 1 minus n per second. Are we very clear, sir? Where n is the order of the reaction. Okay. Now, the third aspect about rate constant is greater is the magnitude of rate constant, greater is the rate of reaction. So you appreciate that rate constant does not depend on the concentrations, but rate constant depends on temperature, and the rate constant magnitude indicates the extent or the rate of the reaction. Fantastic. Now, the famous Arrhenius relation, K is equal to A e to the power minus Ca by RT, indicates the variation of rate constant with respect to temperature. It is called Arrhenius equation. And of course, A is Arrhenius constant and EA is supposed to be energy of activation. And roughly to say energy of activation means if you are converting A to give B, according to the collision theory, there are so many theories that can explain how the reactions proceed. One such theory is collision theory. It proposes that the reacting molecules hit each other and the collisions lead to the formation of product. All collisions will not lead to the formation of product. Only certain collisions that lead to the formation of product are called fruitful collisions. And the A and A keep on hitting each other and their hits are collisions. If they are fruitful, they convert themselves into product. Notice that for a collision to be fruitful, the colliding molecules must have certain minimum amount of energy, and that energy they need to have in order to have fruitful collision may be higher than the normal energy they are associated with. For example, you wish to buy one Lexus car whose cost is 60 lakhs and you have 30 lakhs, and now you require 30 more lakhs, that is energy of activation, the banks will give you as a loan, provided if you have some conditions, if you can satisfy. Notice that the threshold energy required or the money required to buy your Lexus car, which is 60 lakhs, but the normal condition you have 30 lakhs. The difference between these two, that is 60 and 30, is known as energy of activation, that is provided by bank. Here also the molecules, they have some normal energy. To get that threshold energy required to have fruitful collision, the difference between this threshold and the existing energy of molecule is called energy of activation. In a graphical representation, one can show that if this is the energy of molecule, let's choose blue color of course, if this is the energy of the molecule, and this is the energy state that is related to what is called as activation complex. When the A molecules successfully hit each other and lead to the formation of this unstable activation complex, which is of higher energy, then eventually quickly that dissociates to give B the product. Now notice that the energy difference between this reactant and the product, if you observe, the energy of B minus the energy associated with the A, that is of course known as heat of reaction. Notice, in order to have a transition state which is very unstable, which is momentary, that leads to the formation of product. In fact, you can't really separate the transition state. It is not isolatable. In order to achieve this transition state, the reactive molecule should have certain minimum amount of energy. That energy, this A, which it needs, is called energy of activation. This energy of activation is somehow related to the rate constant, the details of which we may see later on. At the moment, I wanted you to notice that Arrhenius gave a relationship using his concepts of thermodynamics, and he gave the relation like K is equal to a constant into e to the power minus E A by RT, where T is the temperature in absolute scale, or is the universal gas constant. E is called energy of activation and A is a Arrhenius constant. Okay, we will not be worried of that now. At the moment, I wanted to say K is related to temperature. And one another important idea we need to share. Most of the time, if you are carrying out a reaction at a T degrees, T Kelvin, if the rate is K, if you are carrying out the same reaction at a T plus 10K, for a rise of temperature of 10 degrees, the rate constant value usually doubles. Rarely it may also become 3 times. The extent to which the rate constant rises for a rise of 10 degrees is called temperature coefficient. Okay. For many reactions, the temperature coefficient is 2. That is, the rate of the reaction doubles, it means 100% increment. Sometimes the temperature coefficient can be even 3. That is, the rate can become 3 times. It can have 200% increment for a rise of 10K. Now, based on these ideas, we can solve some simple problems. Let us see. For a certain reaction, P plus Q gives rise to R. The rate, the initial concentration of A is taken as X moles per liter, and initial concentration of Q is Y moles per liter, and the rate constant is found to be Z liters per mole per second. And now the overall order of reaction is, answer is X, second option is Y, third option is X plus Y, and the fourth option is 2. What is your answer, sir? Obviously, we already stated that units of rate constant are moles per liter whole to the power 1 minus n per second. And now the given units of rate constant are liters per mole per second. See, in the given units of K, there is mole to the power minus 1. Can you see it clearly, sir? Notice moles per liter. Here, mole to the power x, liter to the power minus 1 into x. If you think like that, is equal to liters per mole. It implies x value must be equal to minus 1. Can we see it, sir? If x value is minus 1, then only it would become mole to the power minus 1, then only it will become liter to the power minus 1. Therefore, I would say that 1 minus n is equal to minus 1. It implies that minus n is equal to minus 1 minus 1. N is equal to 2. Therefore, the units of rate constant clearly indicate that the order of reaction, overall order, is 2. But individual orders with respect to reactant P and reactant Q, really we don't know. Overall order is 2. That is inferred from the units of K. Can we clearly see it, sir? So this is one kind of question. Second kind of question, for a reaction, A gives rise to B, rate constant at 25 degrees centigrade is 2 into 10 to the power minus 2 moles inverse liter per second. Now, my problem is, if temperature coefficient tau is equal to 2, what is rate constant of reaction at 55 degrees centigrade? Are we very clear about this problem? For a reaction A gives rise to B, they gave rate constant at 25 degrees. They wanted to know what is rate constant at 55 degrees centigrade if temperature coefficient is 2. Obviously, because the temperature coefficient is 2, reaction rate is going to get doubled for every rise of 10 degrees. So there are two methods. One method is, when you go from 25 degrees centigrade to 35 degrees, there is one rise of 10 degrees, 35 to 45, another rise of 10 degrees, 45 to 55, another rise of 10 degrees. For every 10 degrees, as you said, temperature coefficient is 2 means the rate constant will become 2K here. Again, it will become 4K here. Again, it will become 8K here. Obviously, the new rate constant will be 8 into original value of K. That is 2 into 10 to the power minus 2. 0.16 liters per mole per second. Notice that this is one deduction method, or otherwise you can have a formula like new rate is equal to new rate constant, or rate is equal to original rate constant into temperature coefficient to the power delta T by 10. So here original rate constant is 2 into 10 to the power minus 2, and delta T, change in the temperature from 25 to 55, it means 30 degrees by 10. All this is raised to the power 2, because 2 is the temperature coefficient. So 2 into 10 to the power minus 2 into 2 to the power 3, that is equal to 0.16. If you want to, units will not change, liter per mole per second. If you want to look at the formula, you can obviously see new rate is always equal to original rate into temperature coefficient to the power delta T by 10, because temperature coefficient signifies number of times the rate is going to increase for a rise of 10 degrees. So this is a relationship you can work out. Now you get a doubt, sir, I have a reaction, A gives rise to B, but B gives rise to A, there is an equilibrium situation. The rate constant for A to B is K1, for B to A is K2. So what is the overall rate constant in this case? If we have two rate constants for opposing reactions at equilibrium, overall rate constant is K1 plus K2. Also notice, if a reaction proceeds in two parallel ways, A to B, A to C, if there are two parallel routes in which reaction can proceed, many reactions can happen in this way. For example, if you have benzene diazonium chloride, when the benzene diazonium chloride is reacting with ethyl alcohol, can you guess what are the products, sir? There are two paths, path 1, path 2. In path 1, you get a product like benzene plus nitrogen gas plus HCl plus CH3CHO, acetaldehyde. Then in the second path, the product is different. As in the second path, the products can be like ethoxybenzene plus HCl plus N2. So in the first path, if you say rate constant is K1, in second path rate constant is K2, overall rate constant is K1 plus K2. In this case also it is like this. Sometimes you can have reactions which proceed in steps. So there are first step, second step, third step. Here rate constant is K1, here rate constant is K2, here rate constant is K3. Then what is the overall rate constant for A to become D means? It is given by overall rate constant is equal to product of K1 into K2 into K3. All these are certain facts. They are worthy to note. Okay. Also, you should remember that it is possible to find the order of a reaction by inspecting the units of K. That is one of the methods. So there is a small talk about the rate constant. As your exercise, you can think, for a certain reaction, rate constant is 2 into 10 to the power minus 3 per minute. The order of this reaction is, can you guess? If temperature coefficient for a reaction is 3, if rate constant at 0 degree centigrade is 3 into 10 to the power minus 2 moles per liter per second. What is the rate of the reaction at 20 degrees centigrade? Can you find out the rate constant? So these are some practice problems you can think of. If you want to know quickly the answer for this first problem, the units of K are indicating that it is first order reaction. Here there are two installments. For each installment, rate increases 3 times. So overall increment in the rate is 9 times, that is 0.27 moles per liter per second will be the new rate. Thank you very much. We will be meeting in next lecture.